Hey everyone, I want to talk about today how you can create your own neural network. But before we can actually hop into the code, we really need to see how the data structure works behind the scenes so we can really understand how we learn. So first off, a neural network is made up of three main sections. You can see here the input, hidden, and output layers. Generally speaking, your input and output layers are both very strictly defined, of very set sizes. So your specific problem might say you should have two inputs and one output. So for example, you can imagine a function might have one input and one output if you're in just algebra. The hidden layer is very loosely defined because each layer here is, like, say this one with three nodes is one layer with three nodes, but then here is another one layer with two nodes, and here's another one layer with two nodes. So you can have, say, 100 hidden layers, each with thousands of nodes, and all of that is usually hidden from the developer, or all of it is kind of behind the scenes, and that's why it's called hidden layers. So generally speaking, you have connections going from left to right. So even though you see these very pretty diagrams, this left to right connection is perfectly legal. You just don't see it very often because it's less pretty in diagrams to do these fully connected neural networks. So this is perfectly legal. This is fine. This, however, is less legal because this is just an up-down. So which connection or which node is on the left side? We really can't tell. So any sort of up-down connection is certainly not supported. All connections must flow from the left side to the right side. So let's look at a node, right? We have all these nodes and all these connections, but what operations are actually going on at each node? So we're going to zoom in here, and we see that a node is made up of two main parts. So as the values come in from these connections, we have the summation side that adds up those values. And then after we sum the values, we call the activation function. All right, and once the activation function is done, and we'll talk about that in a second, the outputs are then sent to the next nodes. So what is an activation function? Here is just a straight line, linear y equals x, and this is what you might expect to see if you have no activation function. So what you sum up, if you sum up 1, you're going to get 1. If you sum up 2, you're going to get 2. This isn't great because if you have a linear function and you add another linear function, all you're going to get is a linear function. So what if you wanted to replicate something complex, like a sinusoidal function or anything with any sort of complex curve to it? All of a sudden, this linear function is inadequate to solve the problem. So how do we solve this? How do we create activation functions? For today, we're going to look at ReLU, which is basically a really, really simple and basic solution that allows y equals x, which is really simple, but then once we get to negative numbers, we just cap it. So -1 gives us 0, but +1 will give us 1. In reality, we see a lot of machine learning people love sigmoid functions. This is a really nice function because it clamps values really nicely between 0 and 1. And it's very popular as well because you can train really well around this center point where the slope is high, but then it kind of evens out when the slope is low. So it makes it very stable. All right, so let's use neural networks somehow. What are we going to solve? So this is a truth table, and this is for XOR. This is for exclusive OR. So you can see we have two inputs, and when you put those two inputs together, they create the one output. So we have two ones, and we expect to see a 0. We have one 1, and we expect to see a 1. Two zeros, and we expect to see a 0. So the exclusive OR function can be summarized as if there is one 1 in your inputs and only 1, then you will see a 1 in the output. So how can we make this neural network? I'm going to go ahead and cheat, and I will give you the answer. So here we have a relatively small neural network. This is about as small as it gets. And we're hoping to put in two values, so in this case 1 and get out a 0. So how can we customize our neural network in a way that we actually do get 0? So if we go to this next slide, I'm setting up the weights. So you see that every single connection here is going to have a weight of 1, just to keep things simple. And I will very specially set this weight to -2. This means that any value in, say, this leftmost node, before it gets fed into the next node, it will be multiplied by 1. And same thing here, as we have a value in this node, it'll get multiplied by -2 before flowing into the output node. All right, there's one other thing we have to talk about, and that's the bias of a node. So after you sum up the values of your input nodes, we also can add a bias value, or in this case, subtract 1. I'm going to have no biases on any of these other nodes because for this problem, we don't need any biases. But for the center node, this one hidden one, we need to have a bias of -1. All right, so let's actually try and feed 1, 1 through our neural network, and let's see what happens. So we set 1, 1, and now we have to flow from left to right. So the first node on the left side is going to be this hidden one. All right, so we see that we get this equation where we have the activation function, right? ReLU is just max, 0, and your sum value. And we see input 1 times 1 is associated here. And input 1 times 1 is associated here. And then we have our bias value. So we expect to see 1 plus 1 minus 1, which is 1. And then when we take the maximum value between 0 and 1, of course 1 is bigger than 0, so this node is now set to a value of 1. All right, now let's continue. So we keep going from left to right, and we only have one more node to fill. So now we have to sum up all of the values. So we have 1 times 1 equals 1. 1 times 1 equals 1. And then we have the -2 times 1. And of course, we then get 2 minus 2, which is 0. So we're going to balance out to 0. And this is exactly the output we want it to get. So you can see we can create these neural networks from scratch, though of course that's not the best solution because that takes a really long time. And of course we can also go through these calculations by hand, but again, it's time consuming. Neural networks are really an optimized structure for computers to use. Obviously us using them directly is pretty useless. All right, but that's going to be it for now. You should definitely watch the next video on actually implementing this neural network in code.